Hello. So we are a red team, and we are in charge of the transit from Earth orbit to Mars orbit, and then Mars orbit to Earth orbit. So bonjour, I'm Mathieu from France.
Hi, I'm Holly from the Isle of Man. I'm Anastasia Arkova from the US.
Ram, I'm Divyansh Kaushik from India.
I'm Janet Ndiaye from Senegal.
Hi, I'm Karen McKinnon from Scotland.
I'm Aliman from the USA.
And I'm Linus from Namibia.
Okay. So what's the main aspect of a mission is about this trajectory, about this timeline. So that we have designed. So our mission is comprised of 413 days. That is a 3-month transit from Earth to Mars, staying on Mars for around 7.5 months, 249 days, staying there doing exploration, everything like blue and green team stuff. And then we will return from there back at around 17 August into 2040. So that's then back to Earth in 3 months transit. That's 92 days. So this is our timeline. The blue, as per told earlier, we have 2 rockets. That's a blue one. We have depicting timeline using the blue color and the black color. The black color shows the crew modules, the crew rocket. That's all designed, and the blue shows the cargo rocket. That's all decided here. So both the rockets will follow the same trajectory, and the trajectory simulation is as per here. So this is the trajectory that we have decided. This is the simulation of planets around 1 May. That's this is the trajectory that we have decided. So our rocket will launch around 1 May in 2039. Then we have 7.5 months staying on Mars, and then we will return from Mars at around 17 August in 2040. So this is the whole planet's trajectories will look like.
So as previously mentioned, we will have 2 rockets, 1 cargo ship, 1 cruise ship. The cargo rocket will include the rover and 3 additional landers, and the cruise ship...
Hey folks, St. Augustine, Florida, wow. Denver mission?
Sorry about that. I will not be giving you a lecture in St. Augustine. Sorry, back to the rocket design. And as I was saying, the cruise ship will include the lander and the crew module. On the crew ship, there will be artificial gravity simulated.
Okay, so for the major systems, this is pretty much our rocket laid down flat. For the propulsion system, we're going to use the Vasmir engine, the latest engine model under development. Power, we're going to use nuclear generators, solar panels. For life support, we're going to be thinking about the atmosphere, some clean water. We're going to have food, supplies, crew quarters, exercise, workstation, sleep, microgravity. For protection, we got radiation protection and thermal protection. For navigation, we're using the Deep Space Network and START field. For communications, we're gonna be using the Deep Space Communications.
So for the power supply of the transit vehicle, we will use 2 main power sources. So the nuclear thermionic avalanche cell, and then the metal-junction thermoelectric generator, so NTAC and MJTE. So they have a few advantages, like high efficiency, enough power for Casimir, will last the entire mission without refueling,
have stable power output and can operate in microgravity, even if we will have artificial gravity, and are very scalable.
So, because this is nuclear energy, there are also some disadvantages, such as high excess radiation and heat. But also, our power unit cannot be turned off easily, and in case of an accident, there will be an increased risk. To minimize these disadvantages, we've come up with a few solutions, such as using carbon nanotubes filled with polyethylene to reduce the radiation and heat leakage, as well as actually converting both to electricity, acting as both insulation and also our power generation.
So for the cruise ship and the cargo ship, we will also be using solar panels. So there will not be the primary source of electricity, but we will be using them for provide emergency power and to start the main power sources and then the engines. So it's also to power the fuel while all the power is offline, and we will be using the Red Wires warning out solar array, so ROSA, which has high efficiency, low profile, and proven technology, as they are also using in the ISF. And the estimated draw is of 160 kilowatts, as we will be using 4 panels with individually 40 kilowatts per panel.
So, this is now our power supply system that you heard a lot about. And at the moment, almost all of this is only theoretical, and a large portion of our budget and time are going to the development of this. So what you see here is a core of uranium-235 enriched to about 20% at the center. This will emit both heat and radiation, and we can actually convert both to energy. So our Antac cells surround the core, and as already explained by Luke, this is going to convert the gamma radiation to electricity. And then around that we have the MJTE, which basically uses a combination of metals to get electrons going, which also produces electricity. Then, because we need a difference in temperature and also to prevent our system from overheating, we'll have heat radiators just to, keep everything going. We decided on this system because it has a very high power output at an energy density of about 30 kilowatts per kilogram, which means a 1-ton reactor will provide us with 30 megawatts of electricity, which will be enough to power all our systems and even more if we ever needed any. And yes, it is also very good in terms of, weight because of its efficiency, but also because we need less shielding, as it kind of acts as its own shielding already. Next slide also mine. Right, so this is kind of an explanation on why we chose the propulsion system to be the way it is. So the fuel accessibility, we chose to use argon as our propellant because it is in Mars' atmosphere. Actually, by our calculations, we concluded that we will not need to refuel, but in case something comes up during the development, we have options available. Then also, we needed our propulsion system to be able to provide both high thrust and also operate under high efficiency, which is why we chose the Vasimir, which is very efficient, and then upscaled it to be able to cover our needs and thrust. Then obviously we'll need RCS for minor adjustments and also maybe the docking maneuvers. And the Vasimir 3D thrust vectoring is useful for this, but also we can use argon gas for cold gas thrusters, which is a more downscaled approach to this problem. Then all our systems should be operable in a vacuum, and they should be able to reignite anywhere at any time, which they do very well because they don't need ignition, and they also don't need oxygen or any other gas or pressure from outside to work. Then the low fuel requirement, again, because of the Vasimir's efficiency and also because of our nuclear power source, which means that we will have to bring very little fuel and we will not have to refuel.
For the assembly in space, for both rockets, we're gonna assume that the advancement of our tech is going to be much better, and we're going to use Falcon Heavies to take each module of each rocket into the parking orbit, which is the smaller dotted circle closer to Earth, and then it's going to be assembled from there.
So for the assembly, we'll use the Falcon Heavy as you say, and it will be from the bottom to the top, like backwards and first. So and it will be in 10 launches split in over 5 days, and we'll use 2 launches which are Boca Chica and Cap Canaveral. And since the tugs are heavy, we'll have to minimize the number of back and forth each tug makes to make valuable the use of multiple tugs.
This is just a simple representation of our plan. We're going to have the Falcon Heavies take off from the ground, obviously, and go take the modules up to low Earth orbit, and then the modules or the space tugs are going to collect the modules and put it into the parking orbit, and then put them together from there. And on the side is just a timeline of what we're using, the dates that we're going to launch each rocket. CC is Cape Canaveral and BC is Boca Chica. Those are just the dates that we explained we were going to use.
We will conduct several experiments in both during transit and during orbiting. As previously mentioned, 2 people will stay in orbit of planet Mars. During transit, we will conduct medical studies, which will include blood tests and psychological evaluations. Then we will also closely observe spaceship performance, which will include the technical aspects and the life support system. Then we'll also observe solar flares and magnetic activity using H-alpha monitors and helium magnetometers. And then during orbiting, we will conduct close observations of the moons of Mars. We will research atmospheric composition, which includes atmospheric density and the elements that make up the atmosphere of Mars, and we will take pictures of the clouds on Mars because they provide valuable information about the atmospheric composition of the planet as well.
So on the crew module, we'll have 2 separate floors, each with airlocks between them to minimize tech issues. If something goes wrong on the first floor, we can lock it off from the second floor. There will also be fold-out beds and a fold-out table so that we can maximize the space during the day. There will be privacy sliding curtains around the beds and around the med center so that we can separate it off, and it can also be used as an isolation chamber should anyone get ill. There's also support beams throughout the whole thing, as there are very thin floors, and there are going to be 6 windows spread evenly across the 10-meter depth. The walls on the very outside are only 0.25 meters thick, so there's ample room for the protection systems.
And as for the protection system, we will use Kapton tape as a basic thermal protection. Then we will use a 3-dimensional multifunctional ablative thermal protection system for insulation. And then we will use secondary insulation, which will consist of foam and cork for hardware and for our argon tanks to keep the argon liquid.
And for radiation protection, we'll use titanium alloy and carbon nanotube filled with polyethylene. Polyethylene, used as a matrix material of carbon nanotubes, provides remarkable mechanical and physical properties due to their size and topology. Titanium alloys have a high strength to weight ratio because of its low density and its high specific strength. It also is an excellent it also is an excellent temperature. It also have an excellent temperature stability and a good resistance and weldability properties.
So for the budget and cost distribution, the total budget given to the red team, us, by the yellow team, is $95 billion. We're using $91 billion of the budget given, and a big chunk of the budget is gonna go to the development of the Vasmir engine. Because over the next 15 years, the engine wouldn't be ready unless we budget into it. And for other propulsion, we're gonna have 1.5 billion. Those include small thrusters, which are gonna be set on the size of the rocket. And those are gonna be on to generate artificial gravity. For the power, 11.5 billion. It's gonna go to the NTAC and NJTE development. For the hull, the biggest part of the rocket, it's gonna take $6 billion. And habitat, 9 billion. Human needs 7. Facilities, 5.5. Electronics, 5. Put into orbit, the space subs and the Falcon Heavy, 13 billion. Rocket assembly, 15 billion, and other systems, 6.2.
Okay, so except the trajectory, the guys call us the propulsion guys. Except the propulsions, we have so many additional topics that we should have care upon. So first of all, we have communications, emergencies, including hazards and risks, and interplanetary flight dynamics and controls. And like for microgravity issues, we are using the artificial gravity concept in our spacecraft, and we have different radiation hazards as well. We are using duct tapes on the spacecraft, outside of the spacecraft, to prevent it from the microgravity and micrometers. So in that case, we have a slide for we have calculations slide for every of the topic, but we were supposed to choose 2 of the topics and give official slides to them. So we have that, and that will be emergencies and artificial gravity that team members will be showing upon here.
So for the microgravity issues and preparing for Mars gravity, we have shown that Earth gravity is 1 G and Mars gravity is 0.38 Gs. So the difference is 0.62 Gs, and we have to share these Gs out of the 90 days of travel. So in this graph, we have in blue the proportional decreasing of the gravity, and in orange the number of rotation per minute of the ship, which also decreases as the gravity decreases. And for so this graph is for Earth orbit to Mars orbit, and then we will have to increase the gravity to adapt the astronaut to the Earth gravity, and it will be the opposite graph. We are also using some sports equipment, like the Advanced and Resistive Exercise Device, ARED, the T2 treadmill, and the cycle hygrometer with vibration, isolation, and stabilization system, CIVIS. So these equipments are to prevent the bone density loss and the muscle loss. And so they are already being used in the USS, and they are very efficient. So we will use this sport equipment.
For emergencies on the ship, there are some that are genuinely deadly because of the distance away that we are from anyone else, and because of their actual nature, and they will be under the deadly emergencies there. There are some technical emergencies that we will train the crew to deal with, and they will operate under like standard operational procedures, and we'll have contingency plans for all of these situations. And then for illnesses and injuries, as well as testing, we have the pull-down bed with the privacy curtain around it on the crew habitat to ensure that there's like privacy on the things for testing. That's also an isolation chamber, so we can isolate any illnesses. and we'll also keep any contaminated samples potentially in the med lab.
That's just our sources. Thank you for your attention.